Okay, so first I want to make a few notes about the homework. First of all, the post homework deadline will be postponed by 1 week because we are kind of behind our schedule. We haven't covered many materials for the homework 2 yet. So it will be due next Friday instead of this Friday. So you have more time. And the second thing I want to say is about the question I received at office hour about the k-means clustering algorithm. I'm going to use a different paper. So the k-means part, we ask you to show why each of the two steps in the iterative procedure can reduce the value of the objective function. And I talk about the hint of rewriting this objective function. So I'm going to use the notation in the homework so that you can see the connection better. So what we're going to need to optimize the function is two sets. One is about our CI. Okay, so I'll just call this as CI. It's actually the membership of data point I. I go from 1 to n. The others is the set of cluster centers. I call them MK. And K go from 1 to capital K. And given those, I'm going to write my objective function to be minimized. This is the one we use in the lecture. We take the first summation for clusters, like K go from 1 to capital K. Within each cluster K, we take the data points I such that Ci equals K. Okay, and then for these data points, we compute their Euclidean distance between data point xi and the cluster center nk. That's the objective function we use in class. But we can also write this in an equivalent way by just taking the summation over data points instead of clusters. So we take summation for data point from 1 to n, and for each data point I, we take its difference between it and its corresponding center. So the center should be the center of the cluster it belongs to. In other words, we can write the center as MCI, right? CI is indicating the membership. We know each CI takes value 1, 2, K. And each MK is a p-dimensional vector just as each xi. So therefore, I can rewrite my objective function as this. So in the second step, you're going to show that by using this equivalent representation of the objective function of k-means, that update of the cluster assignment, right? By given your centers M1 to MK, you are going to assign each point to its closest center will reduce this objective function compared to the previous assignment. So you're going to do that and it becomes trivial. Okay, so I want to use this problem to basically get everyone familiar with explaining your algorithm using mathematical notations. So this problem, especially the second step, although it's intuitive if you just think about it, but when you want to write it down in a mathematically rigorous way, then that requires some work. So I want to use this opportunity to let everyone, especially our bioinformatics students who want to do some methodological research in the future, right? In the method section, you want to explain your algorithm as clearly as possible. And often you can make things most clear with mathematical notations. So that's why it's very important that you can write the notations in the consistent and correct way. And an issue with a lot of bioinformatics papers is that usually we see a lot of papers whose method section are either not clear or with some notation errors. And we know that these issues will hinder our understanding, making our understanding more difficult or sometimes cause confusions. So that's very important to bear in mind. And the second question regarding homework 2, okay, I'm going to put here. The second question is regarding the standardization, whether or not you will need it before you do clustering. So this is something we are going to talk in more detail when we introduce PCA. But for now, let me just give you some high-level idea. So whether standardization is needed or not depends on whether or not you trust or you want to use the units of your features. So let's say that we organize our data in the matrix form. Usually we put our observations or data points in rows. We call them 1, 2, n for n data points. And we stack the features in columns. Often we call them 1 to p. So that gave us each row as a p-dimensional observation, right? So when you do clustering, okay, so if you want to cluster the rows, the observations, then the question is whether you trust the original units of the features in your matrix. So for gene expression data, especially for high throughput gene expression data, the P features are P genes that are measured together simultaneously in one experiment. So in that case, they have the same unit. So you don't really have a strong motivation to say, okay, I don't trust my unit. I want to make every gene to have the same range. That's one way of standardization. Or I want to make every gene to be all centered at 0 and have standard deviation as 1. That's another way of doing standardization. So you need a justification to make that standardization. But in some other data science applications, for example, if we want to cluster our clients, right? If these are bank clients and they have P features such as their age, that's one feature. Another is their education level. If we encode education level as a high school 0, college 1, and then postgraduate 2, then you know for sure the age numbers are not directly comparable to the education numbers. So if you use their original units, then your clustering would be dominated by the feature whose nominal values have the largest variance. And if you don't want to do that, then you must standardize your features so that they are comparable. So no single feature dominate. But that is for those daily life features. In our gene expression data, usually, as I said, the P features are genes and they're measured in the same units, say TPM or RPKM. So in that case, if you do clustering, then your cluster result or even PCA later, will still be dominated by the gene that has the largest variance across observations. Then your question is, do you want to really have that gene dominate your result? If not, then probably you want to move that gene out of your data before you do clustering. So for example, in gene expression analysis, sometimes we know, okay, the housekeeping genes have, so let's say single cell gene expression data. So here we have N cells, okay? And we know that in the N cells, like some of them belong to one cell type, some belong to another cell type. So although we know the housekeeping gene should be highly expressed in every cell by their function, but if one type of cells are overall bigger than another type, then the housekeeping gene will also have more copies in that bigger cell type. So you will see housekeeping genes have a large variance in themselves, and these may drive your analysis. So if that's something that's not something you really want, you probably need to leave out those housekeeping genes from your data. That's what we call feature screening. You want to filter out those features you're not interested in, or you may want to normalize your data in relation to housekeeping genes. So after that, then the data will only reflect the normalized variance after you adjust for the housekeeping gene variance. So these are all the things people need to consider in data analysis, including how to do normalization, how to do feature selection, and how to do so standardization is part of normalization. So that's what I want to say. So still, it's a very subjective way, and you need to be very clear about the signal you're looking for, or what features do you really want to use to distinct your observations, then to do the analysis. And that's a general challenge for unsupervised learning, including clustering and dimension reduction, because there's no label for you to use to guide your choice. You have to really be sure about the effect of every step. That's about homework problems. I think these two answers are useful for everyone here. Okay, so then another thing regarding the final project data, I'm going to also give you an introduction here, is regarding that data format. So I received questions regarding that data format because it's not a matrix, it's something called Surrat object. It's something we use a lot for single cell data analysis, because Surrat is a very popular pipeline that people use. It has a lot of functionalities. It's very inclusive. I think a fun thing is that it kind of transforms how the bioinformatics field works. Previously, people have develop individual methods for specific tasks. And so you may use this method for this task, that method for that task. But Surrat just integrates all the popular methods into one pipeline. So whenever a method was published and became popular, it was integrated into Surrat. So then people will use Surrat for a lot of analysis. I think that makes it very convenient for users. So for our final project, so the thing I want to emphasize is that I hope that how can you show your project really stands out? That requires your careful thoughts, like the problem formulation. That's the key. You want to ask an interesting question, and you can use this data or some additional data and to answer your question. It could be a methodological question, it could be a biological question. But what I don't want to see is that you just follow a Surrat tutorial and repeat analysis on your data, because that's just like engineering, or you're just doing like step by step, but it's not really, it doesn't reflect much of your thoughts. So that's the thing to keep in mind. Ask an interesting question. And regarding the data structure, so I encourage you to use Google to help you answer a question. So for example, here I search for counts from Surrat object. So this is a forum, this is a BioStar. It's a very good bioinformatics forum. It has a thread that's showing how you can extract that count matrix. You can have a cell by gene count matrix from the Surrat object. So if you are more comfortable with working with that matrix, you can do this. Okay, so then you will have a count matrix, and that can give you more flexibility. You are no longer restricted by the Surrat functions. And I'm going to post this to the recording. So below the recording, and also I'll also do that on the CCLE, so you can have the link to check out. So there are many similar things you can check online, you can find online. Given the popularity of the single cell field, you can find a lot of things online. Yeah. So I would say for the final project, if you're interested in saying combining common wisdoms or a lot of maybe contradicting sayings about the single cell data analysis, that will also be a very interesting question. Like, do you really want to do normalization on cells, or do you don't want to do that? So if you can find some interesting perspective on that, that can also be a project. All right. So let's come back to our lecture, hierarchical clustering. So this is where we stopped last time. So as a recap, the hierarchical clustering is an agglomerative clustering. You start with n data points and you gradually merge data points into a cluster. So at every step, you reduce the effective cluster number by 1. So you start with n clusters, each cluster containing 1 data point, and then you combine 2 data points to have n minus 1 clusters, and finally you will converge to 1 cluster. And so to let the hierarchical clustering work, you need to have a distance metric between data points, and you also need a distance metric between 2 clusters. So for between data points, you may use, say, Euclidean distance or the L1 norm distance. to measure two p-dimensional vectors. And for the cluster, between cluster distance, it will be based on the between data point cluster. So we have three typical between cluster distances. One called single linkage, means that between two clusters, you calculate all their pairwise distances between data points, one from each cluster. And among those pairwise distances, you pick the minimum as the between cluster distance. That's single linkage. Complete linkage is on the opposite side. You take the maximum of the pairwise distances. You call that the complete linkage distance between two clusters. And group average is the average of all pairwise distances. So this definition, whether you use say Euclidean or L1 norm for between data points distance, or whether you use single linkage, complete linkage, or group average for your between cluster distance, their combination will determine how the hierarchical clustering result you will obtain. So let's give you one example to show you how it actually works. So here, let's give you, as in our notes, here we have 5 data points. So we just have data points in 2 dimensions for simplicity, because 2 dimension is the case where we can draw our data points. So the first dimension is here, and the second dimension is here. So let's say the 5 data points have pairwise distances as follows. Let's call them x1, x2, x3, x4, and x5. So these are the 5 points in the 2-dimensional space. And we measure their pairwise distances using the Euclidean distance. So I'm just here trying to make up the numbers, which may look a little different from the what you see. So let's say x1, x2 has distance 1, x2, x3 has distance 4, and x3, x4 has distance 2. And each of them has a pairwise distance with x5. So let's say that x1, x5 has distance 5, 2 and x5 has distance 5.5, 3, 6, and 4, 7. So given those pairwise distances, I'm going to merge them into, I'm going to do hierarchical clustering by hand. So what I do is that I first put my data points here, x1, x2, x3, x4, and x5. So what I'm going to draw is what we call the dendrogram. This is the thing you're going to see when you plot the heat map by default in R. So the y-axis shows the distance, and it starts from 0. So it will mark when I merge 2 clusters or 2 points, what is the corresponding distance I'm merging. So in the first step, looking at the 5 points, I'm going to pick the 2 that are closest to each other. And obviously it's x1, x2. Their distance is 1. So I'm going to merge them first. So merge them into one cluster, and I mark the distance as 1. So now I'm left with 4 clusters, 1, 2, 3, and 4, right? X1, x2 is one cluster already. Now I need to calculate the distance between this cluster and x3 and x4, x5. So I'm going to use the single linkage. Okay, single linkage will be used. So therefore, given this cluster, I have 4. I need to compute its distance with 3, 4, 5. So using single linkage, I pick the closest distance, right? So between cluster and x3, the distance by single linkage will be 4 because x2 is closer to x3. And clearly, the single linkage distance between the cluster and x4 will be larger than 4 because x4 is farther away. So we don't consider that. And x5, single linkage distance with the cluster will be 5 because we're picking the minimum of 5 and 5.5. So 5 and 4, comparing these two, 4 is smaller. So I know I should merge x3 So if I want to merge x3 with this, it'll be, so if I compute the distance, it will be x3 and the cluster, and that should be 4. Okay. And then I can also consider whether x4 should be merged with x3 and x5, x3. So we compute their pairwise distances as well. So I'm going to mark what we have here. So their distance is 4. Okay. And x3, x4, their distance is 2. And x3, x5, their distance is 6. x4, x5, 7. And this cluster x5, it's 5. So comparing these 5 distances, I can see, okay, x3, x4, they are closest to each other. So their distance is just 2. So next, I'm going to merge them into one cluster. And their merging distance is 2. Okay, that's the second cluster I get. So now I'm left with 3 clusters, x1, x2, 1, x3, x4, the second cluster, x5 only. So just 3 things to compare distances. Now by single linkage, the distance between this cluster and this cluster is 4. And between this cluster x5 is 5. Between this cluster x5 is 6. So now I see I need to merge those 2 clusters whose distance is 4. So I'm going to mark the distance, and they are going to be merged at 4. Okay, so finally, I'm left with 2 clusters. These 4 are in one cluster and only x5. So what's their distance? Comparing this cluster to x5 by single linkage, the distance is 5. So I'm going to do the final merge at distance 5. Okay, this is the result I would get by hierarchical clustering with single linkage. So you can show that, you can see that at every merge, I reduce the number of clusters by 1. And depending on where I cut my tree, I can get a different number of clusters. So if I cut the distance between 4 and 5, I will get 2 clusters, these and the singlet. If I cut the distance between 2 and 4, I'm going to end with 3 clusters, this, this, and this. If I cut between 1 and 2, I can get 4 clusters, this, 3, 4, 5. And then if I cut here, I'm going to get 5 clusters. So hierarchical clustering can allow you to get any number of clusters from 1 to n. And this is not something, for k-means clustering, you don't have this nested structure. So you will not have, say, if you choose k equals 2 versus k equals 3, it is not necessary that for k equals 3, you are splitting one cluster from k equals 2 into 2 clusters, into 2 subclusters. It's not like this. But for the hierarchical clustering, you have this nested structure. You know that when you go down the tree, those new subclusters were divided from a bigger clusters up there. So that's what we say by hierarchical clustering. And there are advantages for hierarchical clustering, as you can see in the notes. First, it's very fast. Computationally, it's very efficient. And there's no iteration at all. You just need to record your pairwise distances, and you need to do some ordering to pick the minimum. And you know that once you merge 2 clusters, so let's say in the pairwise distance, let's say you originally have an n by n pairwise distance, right? Each entry, maybe I should write it down. You start with a pairwise distance. It's an n by n matrix, and it's symmetric. That's a property for a valid distance metric. So what you will do is that once you pick the minimum entry here, okay, so if you pick an entry, that's the minimum here, then you find this corresponding I and j, the corresponding, or I and I prime, the corresponding 2 data points that are closest to each other. Then you're going to stack or reduce them into one row. So for example, after the first merging, you are going to have just an n by 1 by n by 1 matrix. And what you did is that you take the row I and row I prime. You delete one row, okay? And for this, after that, you have only one row to represent both I and I prime. And what you will do is that you will pick the minimum between I and every other data. You will take for every other data point, you will pick their minimum for I and I prime. Maybe I'll draw it. Okay, so let's say this is I prime. You have two rows. And what you will do is that you will take the minimum of the two numbers in each column and put that new number into the new row corresponding to I and I prime. Okay, you pick the minimum for single linkage. And also you do that symmetrically for the corresponding column because it's always a symmetry matrix. So by doing that, you can just continue reducing your pairwise distance one by one until you finally just have one number for the one cluster. So you can see it's very computationally very efficient because you don't need to do iteration at all. And it doesn't require a pre-specified K. You will just get a dendrogram no matter what. And you will just cut the dendrogram given your desired K. Okay. But on the other hand, it has drawbacks. The obvious drawback is that if you do have a pre-specified K, say K equals 4, then the 4 clusters you cut the tree to obtain will definitely have a bigger, no less than within group variance than the one you have with k-means. Because for k-means, that within group variance is the objective function you want to minimize, right? So that's what k-means aims for. But here you don't have the objective function at all. So if that is your goal, you should use k-means instead of the hierarchical clustering. But for our heat map function, why does it implement the hierarchical clustering by default? The reason is that it really wants to make your histogram look nice. By making it look nice, you try to put the similar rows together and similar columns together, so you will see pattern more clearly in the reorder heat map, thanks to hierarchical clustering. Yeah, that's the reason. And also it's very fast, so it's very easy to implement. So you will not make you wait for too long to get a heat map result. That's it. Okay, and bear in mind that this pairwise distance we'll come back to it very soon. So we'll just know it's an n by n matrix and it's symmetric. And also every entry is non-negative, right? That's the definition of distance. So one thing I want to talk about next is a variant of tight clustering. So that's something you can use for finding really tight clusters. So this is a 2005 paper. It's not in the notes, but I'll just write it here. It's a 2005 paper by Dr. George Sung, who is currently in University of Pittsburgh with his PhD advisor, Dr. Wing Wang, who is in Stanford University. So they developed tight clustering method so that you are going to find tight clusters for just a subset of your data points. So there are two motivations for doing this. So first of all, we want to find tight clusters only. We don't want to have very big clusters. And second, we don't want to assign every data point to a cluster. So some data points shouldn't be assigned to any cluster. So you can imagine that if we have a p equals 2 plot again, so still p equals 2, first dimension and second dimension. So if your data points look like this, then it's possible that you only want to find those two tight clusters, and you want to leave the remaining data points as unclustered. That's the motivation for tight clustering. And it may be useful for biological discoveries. For example, let's use single cell data as an example. You may want to find a really tight, small data cluster, and that may have some important biological function. You don't want to drive your cluster result by some loose points, right? If you set k equals 2 and then you do k means, then it's likely you're going to have two clusters, but each cluster will have some points that are far away from the center. That's not what you want to have using tight clustering. So how does it do? It uses a very interesting idea or technique in statistics called subsampling. So in other words, it helps that by using subsampling, in each subsample, you are not going to have some outlier data points. And then each subsample will give you a clustering result. By repeating the subsampling, you will have multiple clustering results. Then you can aggregate them. And if some cluster that will always appear in your aggregated clustering results, you will think that cluster is stable and tight. That's the motivation or rationale, intuition behind the algorithm. So let's talk about the algorithm in detail. So the first step is to do subsampling. So what it does is trying to subsample, say 70% or 80%. These two are common percentages for doing subsampling. So for example, you can think of 80% as that I leave out 1/5 of my data points unused, and I randomly pick 4/5 of my data points to be used for clustering. And then data points, and you apply k-means. Okay, and then of course you're going to have k centers, just as what we have in for k-means, k centers as k and k p-dimensional vectors. And then you're going to assign the remaining, the unsampled 30% or 20% points to the k clusters. So in other words, the centers were only determined by the 70% or 80% points. After determining the centers, you just do the assignment step. You assign the unsampled data points to the k centers. So therefore, you would divide all your data points into k clusters. Let's say we repeat by capital B times. Okay, so therefore, we would have capital B clustering results. So let's say that you would have, say, I can write this as, if I call a set as a cluster. So I have C11 for the first subsampling, CK1. That's the first run. And then I repeat this for capital B runs. I can have C1 capital B to CK capital B. So these are the results I obtained after repeating subsampling for capital B times, and each time I apply this procedure. That is, use k-means on the subsample data points, apply the unsubsample data points to the k centers. So then I want to assess how stable these capital B cluster results are. Okay, so I want to construct something I call a co-membership matrix. This will be an n by n matrix, just as our pairwise distance matrix. So I call that as capital D. Okay, so probably I should call that here. It's an n by n matrix, and it's symmetric. So let's say that the ijth entry, I call that dij. Okay, then dij is defined as what? The dij is defined as the percentage of times, or I can write it as here. So the number of times, number of runs that ij are in one cluster. So if you look at your results, so you just look at xi and xj, and you see, are they in one ck here? If yes, you record one, record one. And you look through every of the B results, see how many times these ij points are in one cluster. You record a number, and you divide that number by capital B. So this will give you the proportion of runs where data points I and j are in one cluster. So you see, by this definition, the cluster label does not matter. So for example, I and j may be in cluster 1 here, but they may be in cluster K here. Since the labels do not mean anything here, we don't need to align the labels. We just record whether 2 points are in one cluster or not. So this proportion is very important because we know that if 2 points I and j have a high proportion, are appearing in a large proportion of runs, are co-clustered in a large proportion of runs, we think they should stay in one cluster. So then our final result is to find tight clusters from this co-membership matrix. And what do we do exactly? What we do, let me just use this paper. So what we do exactly is to, now we have a useful tool. So let me just ask you this question. So in step 3, so given a threshold, let's say alpha equals 0.7, which means that I really want to put data points which are together with each other for 70% of the runs into one type cluster. I want to find tight clusters such that within each cluster, points I and j have dij greater or equal than alpha. That's the final step I want to do. So that means if I really want to have 2 points, so in other words, I want to partition the co-membership matrix in some way so that I can satisfy that for each resulting tight cluster, within the cluster, all pairwise points have their proportions greater or equal than alpha. Then my question for you is, can we use some technique we just learned to achieve this? How can we find such tight clusters from this co-membership matrix D? You can think about this question for a few seconds. So what does it mean that within each cluster, all pair points have, we can think of this as a similarity, has similarity greater or equal than alpha. Or I can give you a hint. This is equivalent to say all data points have pairwise distances as less or equal than 1 minus alpha, if I define this 1 minus dij as a distance.
Can we do hierarchical clustering and then stop wherever the distance gets over 0.7 for like that branch?
Yeah, definitely. That's the correct answer. And as a follow-up question, for hierarchical clustering, what distance do we want to use for between clusters to achieve this? Look at those three. The single linkage, complete linkage, or group average. Which one do we need for this purpose, for this task?
Would we want complete linkage to make it as tight as possible?
Exactly. The complete linkage is what we want. The reason is that you see, for complete linkage, when we want to combine two clusters, we need to make sure that every pairwise distance between their points are below the threshold, right? That's how we combine the two things. So that's why we can make sure if by complete linkage, we have a cluster, okay? So let's say here, although we do single linkage, but just pretend that this is complete linkage. So if you look at, we cut here, we look at this cluster at distance 4 with x1, x2, x3, x4. By complete linkage, we know that any pairwise distances between points in this cluster must have their distances below 4. That's how they can be in one cluster. So that's why you see, if we do, the answer is to do hierarchical clustering with complete linkage. So with this, if you combine your data points, and then you can say cut the tree, the dendrogram, at 1 minus alpha. So basically, this distance is defined as distance between I and j is defined as just 1 minus the dij, right? Here, 0 means perfectly similar, and we just do 1 minus that. That becomes the distance. So then you can just do that, and then when you cut the dendrogram at the distance corresponding to 1 minus alpha, you will obtain the clusters. And you know that for each cluster, you can make sure points within the cluster have pairwise distances no greater than 1 minus alpha, which means that they have similarities no less than alpha. So that's something you can achieve. So you see, it's very interesting that hierarchical clustering has this very important use for finding tight clusters within a co-membership matrix or from a distance matrix. Okay, so you see that here the tightness, if we revisit the concept, it's not just about whether given data points, whether their Euclidean distances are small or not. Because if we just want that, we could just get the pairwise distance matrix and apply hierarchical clustering with complete linkage to it. Then we can find clusters so that within each cluster, the data points must have pairwise distances no greater than a threshold. You can do that. But in that case, you don't know what the threshold should be, because the distance here can go from 0 to positive infinity. It's a very big range. How do you set a threshold? That's not a very easy question. In the type clustering, what we're doing is that we're not just looking at the pairwise Euclidean distances, but we're looking at the stability of the clusters. So the stability is in the sense that no matter how we perturb our data by doing subsampling, we can always find these points within one cluster by k-means clustering. So that's something desirable. And just for your information, so recently my group, a PhD student of mine, was motivated by this idea, and we applied this idea to the clustering problem in networks. So we call that spectral clustering on network. And so if you're interested in checking that out, we have a research paper called BITSC, published in Bioinformatics in 2020, last year. So essentially, we applied this tight clustering idea with the clustering technique called spectral clustering, which is something I'm going to briefly talk about next. Spectral clustering is a very commonly used technique for identifying communities, node clusters from a network or a graph. So this can be considered as k-means applied to a graph or network. So here the data structure is not a matrix anymore, but instead it's like a network structure. Okay, so I'm just going to make up things here. Okay, so for example, I can say that I have x1, x2, x3, x4, x5, x6. So I have 6 data points here. And the data points are just, the data I have is just a network structure. I know how they are connected with each other, but I don't know any other feature. So this is my data. So for example, a common data structure like this is the social network data, like the Facebook data. You have n individuals, you only know how they are connected with each other. So if you want to identify some, say, communities from the network, you know, by the connectivity. So for the people who are densely connected with each other, you want to call them a community. This is what we call community detection problem in networks. But you see, it's actually a special type of clustering problem, because you are still trying to divide data points into clusters. You call the clusters as communities. The difference is that you do not have your data point encoded as features directly. You just have the connectivity. So for this type of data, we call our observed data as an adjacency matrix. So the adjacency matrix is an n by n symmetric matrix. So standing for the n nodes, okay? And the entry could be, so let's just call that, I call this A, I call this Aij. So the Aij is either binary. 0 means connected, 1 means, 0 means not connected, 1 means connected. Or it could be a value between 0 and 1. That is for something we call weighted network. So for each egg, you do the weight, and the weight can be as small as 0 or as big as 1. That's the data you have. And you're going to do clustering of the n nodes based on this adjacency matrix. That's the problem. So how spectral clustering works? So it's basically based on what we call eigenvalue decomposition on something we call graph Laplacian. So just to give you a very short introduction, I'm not going to into detail for that because this part is kind of technical. And this also is not really the theme of our class. So I'm not going to give the detail, but I want to share you a screen so you can read later. And here it is. So this is a website I really like. I think there are a lot of useful posts for you to look up. It's called Towards Data Science. Sometimes I repost here. So spectral clustering, I think this is the simplest introduction I have seen. Previously, if you search for Google Scholar, you can find a highly cited review paper on spectral clustering, but that is very long and technical. This one gives you a lot of intuition. So essentially, to really understand spectral clustering, you need to understand the eigenvectors and eigenvalues, the linear algebra concept. And then you can think of it as the steps as, maybe I can scroll down. Yeah, this is the adjacency matrix I just said. This is how it looks like in Python. Entries are 0, 1. And you also need to get a degree matrix, okay? By degree matrix, you take the row sum for every row. So here you count 1, 2, 3, 4, which means this node is connected to 4 other nodes. So its degree is 4. And for this one, you take sum 1, 2, so it's 2. So you basically take the row sum, put it into a diagonal matrix called a degree matrix. And then you will define what we call a group Laplacian. This is based on graph theory. What you did is that you do subtraction, degree matrix minus adjacency matrix. Both are n by n symmetric matrix. So this Laplacian will still be symmetric. But you see that except the diagonals are still the degrees, right? Because in the adjacency matrix, the diagonal entries are always 0 since the node is not connected to itself. And other entries is just 1 minus, just the negative of the adjacency matrix, because it used to be 0 in the diagonal degree matrix, minus adjacency. So you have negative ones over there. That's what we call a graph Laplacian. And this is the information you are going to use for your clustering. So what it does is that you try to do eigen decomposition on the Laplacian, you obtain the eigenvalues. So basically, the eigenvalue will tell you information about the clusters. That's very interesting. And you're only going to pick the eigenvectors corresponding to some small number of eigenvalues. And so you see the first non-zero eigenvalue is called the spectral gap. The spectral gap gives us some notion of the density of the graph. If this graph was densely connected, all pairs of the 10 nodes had an edge, then the spectral gap would be 10. So it's actually about whether your network is connected, fully connected, or disconnected. So it's about that. So this eigenvalue can give you that information. And then you are going to use the eigenvectors of the Laplacian to perform k-means clustering. So basically, let's say you pick two eigenvectors, and then given the n nodes, you are, see here, given the n nodes, you are going to have an n by 2 matrix with the nodes in the rows and the eigenvectors in the columns. Then you perform k-means on that matrix. Here you set a number of clusters to 4 so that you can obtain the clusters. This is what we call spectral clustering. And actually the word spectral, the adjective spectral, is often associated with eigenvectors and eigenvalues in linear algebra. So I think this can give you a lot more motivation to really study linear algebra if that's something you are not so familiar with, because it's very important for machine learning nowadays, because a lot of data we work with are in matrix forms. Okay, so that's a very brief introduction to it, just to give you some idea, very basic intuition. And then if you're interested, you can look at the webpage and later by yourself. Yeah, so that website is definitely something worth checking frequently. All right, so finally, we conclude this clustering part based on algorithms. So what I'm going to share that window again. So here, what we have talked so far, the method we talked about so far, are called algorithm-based clustering. Okay, so these are all algorithm-based clustering methods. What does it mean? It means that we just applied an algorithm to our data, and we just operate on our data, and the algorithm does the operation. But we didn't talk beyond our data. We do not talk about which distribution these data come from, or we are not trying to infer the underlying population from which the data are sampled. So that's why, in other words, these methods are not probabilistic. And by the way, the BITSC method my student developed was based on the spectral clustering, but it's applying it to the bipartite network. So that's a special type of network where you have two types of nodes, let's say authors, papers, or you can have drugs, gene targets. So these type of network where you only have an edge between nodes of different types, so that you have an edge from an author to a paper if the author wrote a paper, but you do not have edges between nodes of the same type. If your network is of that type, you call it bipartite network. Okay, so I'm going to move on. So to the next part is what we call model-based or probabilistic-based clustering. So how do we work on that? For that, we need to use probability distribution. Model-based clustering. So in some bioinformatics papers, you will see the word model-based. I think it was started by Wing Wang like 20 years ago, when they say model-based like microanalysis. So model-based here, what it implies is a probabilistic model. So if we think about probabilistic model, it's essentially our hypothetical population. hypothetical population. So what it means is that we imagine, okay, there is a population which is described by a probabilistic model and from which our data were sampled. So then we're trying to do clustering based on how we infer this population or how we infer the probabilistic model. Okay, so in other words, the approach is to, the idea is to cluster data by inferring model parameters. Okay, so that's the approach we're going to take when we're going to introduce. And then this is connected to some topic in statistics we called missing data problem. What's missing here? So if you think about our notation in k-means, we have data points x1 to xn, right? These, each of them are belonging to the p-dimensional space as a vector. That's our data. And we know that these are observable, or we actually observe them. But what's missing here is that they are cluster membership. So by our notation, C1 to Cn. And each of those should be picked from 1 to k. This is the cluster membership, but this is missing or hidden. If these were known, then we are actually in the supervised learning context. We know the label of each data point. For example, I'll use the single cell data analysis as an example. There are methods, there are many computational tools called cell type annotation tools. So what it does is that they try to build a supervised learner, or more specifically, a classifier on single cell data where you have the gene expression vector of each cell and you have the type of each cell. So that will be the cell type. You can train a multi-class classifier, and then you apply it to that to new cell. So for the new cell, given its gene expression vector, you predict its cell type. That's supervised learning. But in unsupervised learning, the cell types are unknown. We just know that we want to find K cell clusters. And then the question is, how do we know which membership each point has? This is a missing data problem. So to start with, let's talk about the Gaussian mixture model, which is the simplest type of mixture model. Okay, so we'll start with the Gaussian mixture model. And this is actually what you have in your homework. So please pay close attention. In the Gaussian mixture model, we have our data points drawn from a mixture distribution. So to make it clear for you, the mixture distribution is specified by the cluster membership. So we think, okay, each cluster corresponds to one Gaussian or normal distribution. And putting the observations together, like some may come from one distribution, some may come from another distribution, then their population jointly is what we call a mixture model. So let's make it simple. Let's just say this mixture model has two components to start with, okay? So we specify that for data point I, there is a hidden random variable Zi that is drawn from a Bernoulli distribution with P parameter. That is the probability of taking a value 1. So that's how we first just think of this as a generated model. So how you generate your model, how you generate your data from this model. The first step is to draw a hidden binary indicator. So this is the membership. indicator. 0 means one component, 1 means another component. And then our observed random variable, we call it z. So here we just make it simple by letting the p equals 1. So we have one-dimensional data. That's easier. So we just say that here when zi equals 0, conditioning on this, we sample the data from a Gaussian or normal distribution with mean mu0 sigma 0 squared. When zi equals 1, we sample it from a different normal distribution with mean mu1 variance sigma 1 squared. Okay, this is a model, and this is what we call the Gaussian mixture model. So you see it's a two-step model. The first step, we draw zi. The second step, we draw xi. So putting it together, we can actually show that the density, so the density probability, I call that PDF. Maybe I'll write it out. Probability density function of xi, okay? So it actually should take this form. So fx should be equal to, just by that conditional probability and marginal probability rule, it should be equal to the probability that zi takes 0 value. So it's 1 minus p times the density of the component 0 times by calling f0x plus another probability when zi equals 1 times p plus p times f1x. Okay, that's the probability density. So it's just the conditional times marginal plus conditional times marginal. The same thing we use in the Bayes rule or Bayes theorem, if you recall. Okay, so this is what we call a mixture density. Because if you plot this density function, you are going to see two modes. One is at mu0, one is at mu1. And this is the thing you can see in our lecture notes posted on Sysdally. Okay, so then the question is, how do we estimate the model parameters? P, mu0, mu1, sigma 0 squared, sigma 1 squared. We have 5 unknown parameters. As long as we can estimate it, what we are ultimately interested in is this thing. So given our, say, observed data being, I'll write lowercase x1 to xn, what I want to infer or want to have is the probability. I'm using the uppercase P to mean it's a discrete probability, not a density. Zi equals 1, conditioning that the random variable xi is equal to the observed value lowercase xi. So this is our data. This is the random variable in our imagination. So in our imagination or our hypothetical population, there are random variables big xi and the random variable big zi. So they are random. Our observed data is using lowercase. So, you know, by Bayes' rule, how do we write this down? This is equal to, right? So this can actually be written as fp times f1xi divided by 1 minus p f0xi plus p f1xi. This is by Bayes' formula, right? Bayes' rule. We have this. Then we can decide whether we will cluster xi into community or cluster 1 or cluster it into cluster 0, right? Defined by 0 or 1 for the two clusters based on this probability. So often what we do is that if this is greater than 0, we would predict zi, so our data point to have zi equals 1, which means that we put it in cluster 1. 0.5. And otherwise, if this is less or equal than 0.5, or you can put the equal sign either part. That doesn't matter that much. Usually it will not be exactly equal to 0.5. You predict zi equals 0, which means that you put the data point I into cluster 0. So doing so, you can divide your data points into 2 clusters using this probability approach. So it seems to be straightforward. But when I said the challenge is that we don't know the model parameters. P is needed here, 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 and F1 needs mu1 sigma 1 square, F0 needs mu0 sigma 0 square. So you can only do this when you know those model parameters. So that gives us an estimation problem. Okay, so far, do we have any questions about this model-based clustering idea? This is the simplest thing for 2 clusters. Okay, so if I want to generalize this to multiple clusters, say K clusters, what I only need to change is that the Bernoulli needs to be changed to a multinomial distribution with just one observation, but K categories, each category with a probability. So I have P1 to Pk, and they sum up to 1. So here for Bernoulli, I have 2 categories only. So because they sum up to 1, so it's 1 minus P and P. I only need 1 P. But for multinomial with K categories, since P1 plus 2Pk equals 1, I only need K minus 1 of them. I don't need K P's, but just K minus 1 P's. And given Zi equal to each number, I'm going to draw the normal distribution. So I will have K, capital K, normal distribution. And then I can compute this probability for each K. So what is the probability for Ki equals K? I can just have it here, change it here. So probably I'll write it down. So just for your convenience. So probably I would just say, now generalize it to K components. Okay, if I do that, then I would have Zi follow multinomial with just one observation to be drawn. And the probability vector, I call it P1 to Pk. And the constraint I need is that the summation of those Pk, K from 1 to K, must be equal to 1. That's the hidden part. And for the observed part, I would have xi given zi equals lowercase k to follow a normal distribution with mean mu k variance sigma k squared. And of course, here the k go from 1 to capital K for my k components. So then my decision, so the distribution, okay, I need to write down this. So the distribution, the PDF of xi, in this general case will be fx equals summation k from 1 to capital K, pk times fkx. That's it. That's the mixture model. And then finally, my decision will be based on the probability zi takes k, given xi equals our observed value, lowercase xi. And we will have pk fkxi divided by this PDF, fxi. That's it. So given that now for every data point, I'm going to have k such probabilities. So probably I can call this, if I denote this as qk. This is the probability that I would believe the data point I is in cluster K, given its observed value. And some people call this as posterior probability. Posterior is often used, we know this in the Bayesian sense, but here it means that we're conditioning on our observed data. We talk about the probability of our hidden variable, which is actually similar to a parameter because VI is not observed at all. We're interested in its probability given our data. So we call this a posterior probability. And then what you will do is that you will assign your decision is to assign data points to the cluster or community or component for which it has the largest QK. So you will just set CI, its membership, to be the K such that QK is maximized. So you want to find the K from 1 to capital K. So you pick the number such that QK is the largest, and then you assign data points to that cluster. Okay, so these, what I said just now, this whole part will be applicable to any model-based clustering. That's just the essence behind it. But usually the challenging part is to how to estimate model parameters. Because these parameters are needed for your calculation of QK. So for this one, the most popular algorithm and very generally applicable algorithm is what we call the expectation maximization algorithm, short as EM algorithm. So we are going to introduce that in our next lecture after we come back on Thursday. Okay, so but I think it's good that if you want to do a preview of the lecture notes 8, for the part which I use the voting as an example to demonstrate this idea about the missing data problem. Although that voting problem is different from the Gaussian mixture, but they are very similar in nature. So that's why I'm going to do the EM algorithm derivation for that voting problem. And in your homework, you're going to do that derivation for the Gaussian mixture problem yourself. So if you understand that, then you should generalize it or apply it to the Gaussian mixture model. Okay, so do we have questions? Oh, and finally, I want to say that the EM algorithm, the essence of it is to do MLE, maximum likelihood estimation. So MLE is just a very, I would say, dominant approach for parameter estimation nowadays. So that's why if we can do MLE, usually we just use MLE. Okay, do we have any questions for what we said in the beginning or what we said about hierarchical clustering and tight clustering, spectral clustering, and model-based clustering? Okay. Oh yeah, one take-home question for you to think about. I forgot to say that, I should. Is that now in single cell analysis, a dominant approach is that we don't do clustering on the cells just based on some cell distances, like a pairwise distance. We don't do clustering on this. What we do is that we don't apply hierarchical clustering or k-means to cells directly. What we do is very interesting, is that we try to reduce or compress this pairwise distance matrix into some sort of a graph, cell to cell graph. And then we use this graph and apply clustering on the graph instead of the original data. So maybe you can keep this question in mind and think why we want to do this and why is this advantageous. And I have to say that there's no firm answer yet, but it's something worth thinking. So if you can think of it, probably I can ask you in the beginning of our next lecture, and I also can offer my own thoughts for you. Okay. So that's all for today. Thank you.